So we're going to come back to this problem now and finally show why this is always equal to this. Okay, so let's go back and prove. And I don't know why we don't use the word prove. We usually use verify or establish. Instead, we use that verb. But we're going to try and finally prove this. So there are so many ways to do this problem. We're going to do it two different ways. I'll do it the first time, and then I'll get you started on the second time, and you're going to try. Okay? So the first thing I'm going to do on this is I'm going to recognize that tangent theta is also known as sine theta over cos theta. And I'm just going to directly replace that. And cotangent theta is also known as cosine theta over sine theta. I'm not allowed to touch the other side because I've already started working on the left. You may not cross multiply. You cannot rewrite this as sine theta over cos theta and try to work it from there. You're not allowed to touch the right side at all. Okay? Some teachers are more strict about that. Some teachers are less strict about that. I'm very strict about it. Pick a side and work on it. Okay, let's see if we can make this work. What you have here is a complex fraction from Algebra 2, right? So most people, not everyone, but most people solve this by multiplying top and bottom by the various denominators you see. So you see there's these two little fractions. There's a sine over cos and a cos over sine. So you just multiply once by cosine and once by sine. That should clean up these little microfractions. Okay? And you have to do top and bottom. Okay, let's distribute. So we're taking this green object and distributing it to these two black objects. Right? So what's my numerator? Well, what's sine theta cos theta times 1? Sine theta cos theta, right? And what is sine theta cos theta times sine over cos? What happens if you multiply this with this?
Sine squared over 1.
Yeah, the cosine's going to cancel out, right? But the sines are going to multiply together. So you're going to get sine squared and the cosine will just drop out. So this is actually sine squared right here. Let's do the same thing on the bottom. We'll multiply the green object with the two blacks. It's kind of nice to color code this. Okay, multiplying the sine theta cos theta by the 1 there, we can just get sine theta cos theta. Yeah, in the second multiplication, this time it's the sine squares, or the sines that cancel off, right here, but the cosines build to form a cos square, see? So, we're still trying to show that this is just tan theta. And of course, there's always the student who does this. Is that legal? No, it doesn't even work. That gives you tan squared equals tan. But it's awfully tempting to try to fake it like that and try to convince me that you know what you're doing. I never fall for this stuff, so please, please don't do that. That is not a legal math move at all. What you can do is factor the top and bottom. The top does have a sign in each term. So let's pull that out. And the bottom has a cosine in each term. Let's pop that out. And now we have a very legitimate and legal cancellation. Cosine theta plus sine theta divided by sine theta plus cosine theta, that's 1. So this proof ends with us actually writing this tan theta equals tan theta. Okay? And if you want to write one more thing, you might want to write this, QED. QED. Does anyone know what that means? Has anyone seen that before? It's actually Latin. It's actually Latin, and it means which had to be demonstrated, or which was to be shown. Fun to write that at the end. That's kind of your little reward, right, QED? If you want to write that, it's kind of fun. Okay? Let's try some of these other identities that they have in the book. So there are a couple other identities, like there's this one, sine of negative theta equals negative sine of theta, and cos of negative theta equals cos of theta, and tan of negative theta equals negative tan of theta. These are listed in the textbook as even-odd identities. Okay? Even/odd identities. But to be honest, they're just a rehashing of the same thing we learned in chapter 2, and that we also discussed a little bit in chapter 5. It's just basically means that since sine is an odd function, right? Sine theta is odd. It has origin symmetry. And remember how f of negative x equals negative f of x is true for an odd graph? Well, here it looks like sine of negative theta equals negative sine of theta. It's almost like we pulled the negative out front. You know, pop the negative out. That's what it looks like we did. Okay? And for cosine, remember cosine is actually an even function, so it actually looks more like this. Not a very good drawing, but it's even, right? But basically the left and right side of the theta axis are the same, like it's a mirror image, so it doesn't matter if you go right or left, cosine negative theta, cosine positive theta, they're exactly the same. Cos 10, cos negative 10, same answer. So on this one, we just basically obliterate the negative. We take this negative and just destroy it. We pretend it never existed. That can simplify a problem with negatives, right? You get to throw them away. That's nice. And then this problem, this one here, the third one, that's tangent. I don't know if you can see it, but the negative's on the front there. This means it behaves like sine. We can pop the negative out. We can't erase it, but we can pull it out front like we did for sine. And the reason is tangent is what kind of graph? What kind of symmetry does it exhibit? Origin symmetry, so it's odd, right? So odd, even, odd means pull the negative out, erase the negative altogether, or pull the negative out, see? Let's talk about the three reciprocal guys. So what about cosecant negative theta, and secant of negative theta, and cotangent of negative theta? What should we do with these? Do we erase their negatives? Do we move their negative out front? Well, turns out you do the same thing with these three that you do with their reciprocals up above. Okay? Cosecant graph looks something like this. That was a horrible drawing. Let me redraw that. This is cosecant theta. Remember from your note cards? This thing's odd, right? So you would actually pop the negative out front. Secant theta is clearly even. You can tell from the symmetry. And so you would actually just obliterate the negative, just pretend it never existed. And cotangent theta, this is a little bit hard to see. Like, what kind of symmetry is that? I don't know if you have your flashcards handy, but if you take out your cotangent flashcard and you lay it flat on your desk and you spin it 180 degrees, it's odd. So cotangent is also odd. So we'll be popping the negative out. So much for the idea that an odd function has to pass through the origin. Some of you wrote that on your first exam. You wrote, the graph is odd because it passes through the origin. No. Look, cosecant is odd, but it doesn't pass through the origin. The origin is actually forbidden. Same thing with cotangent. That doesn't go through the origin, but it's still odd. Something doesn't have to pass through the origin to have origin symmetry. Okay? All right, so are these new? Not really. They're just the idea of odd and even all over again. But it allows us to do a problem like this one. Okay, so look at this problem. This looks really awful. sine of negative theta over 1 plus cosine of negative theta plus 1 plus cosine of negative theta over over sine of negative theta. Can you verify that this really is negative 2 cosecant theta? Because these do not look the same at all. Can you verify? Okay, I don't see a ton of ways to do this problem. I see pretty much one way to do this. I've got to get rid of those negative thetas. I can't handle those. That's going to drive me crazy. So what are we supposed to do with the sine? Pull it out, right? And the cosine, what do we do with the negative there? Just pretend it never existed, right? And this one? Pretend it never existed. Here, pull it out. In fact, I really don't want to carry that negative around for the rest of my life. I'm just going to put it way out here. I'm factoring a negative out. I really don't want to hassle with it. Looks like I've got some fractions to combine. I'm not excited about working with minus signs. So I just avoided the issue, pulled it out. Here I am running for my problems in life. Okay? Then we'll see what I did there. Makes the inside look a little nicer. Okay, I'm going to give you a minute or two to try to combine the fractions. Okay, try to combine the two fractions into one using an LCD. Okay, so on this, you guys, you want to go ahead and try to combine the fractions. So you can use this method if you like. You can multiply this up to here and multiply this up to here. And then the lowest common denominator is obviously just 1 plus cosine times sine. So it would look like this. Sine times sine is sine squared. 1 plus cosine times 1 plus cosine would be written like this. And the bottom is just both denominators. So usually your LCD, it's just like the product of your two denominators. Not always, but you can certainly get a common denominator that way. Just multiply it together. Okay, now, the top, be very careful with that. That 1 plus cosine with a square on it, that needs to be properly foiled. Okay? So you're going to have sine squared plus 1 plus 2 cosine plus cosine squared. So be very careful with that numerator. And as for the bottom, don't even touch it. Just leave it like this. I am really hoping that 1 plus cosine goes away anyhow. I'm hoping to get rid of that thing. So just leave it there factored nicely.
Then you can combine your cosine squared theta and sine squared theta together.
Yes, good. So sine squared and cosine squared add up to 1, right? Look at your Pythagorean identity in purple over here. This is 1. See? So that's a really exciting moment. We're not scared of quadratic stuff. Those sine squares and cosine squares never bother us because we have so many identities for those. So that thing is just 1 that I just circled. And now this looks like 1, I'll color code. So that's a purple 1. Plus 1 plus 2 cosine. I'm going to leave this factored. 1 plus 1 is obviously 2, although the proof for that is 300-page book. Yep. At least one of the books that was written on that subject is 300 pages long. More than 300 pages long. Yeah. Okay, I am so close to done. What I like about my answer, here's what I like about my answer. I'm trying to show that this is negative 2 cosecant theta. Right? I like certain things. I like the fact that I have a 2 on the left. That's cool. I like the negative. There's some things I don't like. I don't like the 1 plus cosine on the bottom. That's bothering me. But can I pull a 2 out over here? Okay, so factor when you can, because factoring, although no one likes to do it, that's what cleans stuff up. Okay? Now you can cancel this out. And you're not quite done. I need you to finish the proofs by writing negative 2 times 1 over sine. And then I need you to write negative 2 times cosecant theta. And then you can write QED, which had to be shown, or which was to be proven. So that was significantly harder. We started off with even odds. We then tried to combine the two fractions. We had a cool moment where sine squared plus cosine squared popped up, but that's just 1. We did a little more factoring, and it all worked out. We knew it would, right? So don't give up too soon.
Will you ever give us a proof that doesn't work out? We have to.
No. No, I wouldn't give you one. I wouldn't give you a statement and say, show that this doesn't work or something. That'd be silly.
No, like show this works, then you go all the way through. And you
Yeah.
realize it doesn't work.
I've done it by accident, you know, but I would never do it on purpose.
Just imagine that test question.
Yeah, no, test. I will double check. I will double check everything, because if it never actually is equal, or if it's a conditional equation in disguise, then you'll spin forever on it, and we don't want that. Let me just say a couple little things about this. Okay, so try this problem again. I'm going to set a timer, okay? We already did this problem. I did it the first time by changing tan to sine over cosine and cotan to cosine over sine. What if instead we had done this, change this to 1 over tan? Use this as your first step and try the problem all over again, and you'll see it works either way. The temptation is to cross multiply. If we cross multiply this thing, it's done. Because when you multiply this over, right, you're going to get tan when you multiply these, and you're going to get 1 when you multiply these. And it will read 1 plus tan equals tan plus 1. The problem is we haven't established this identity, so it's not an equation. When you do multiplication on both sides, that's called the multiplication principle, or no, the multiplication property of equality. We haven't verified the equal sign yet. See? So that's not fair game. This is not a true equals until the end of the problem. See? Good question. Glad you asked. Okay, was anyone able to get this to work out?
Yeah.
Okay, so the goal is to try to clean up the complex fraction. This is a little bit simpler looking than last time because we're not doing sine over cosine and cosine over sine, so we're just changing cotan to tan. So let's see where this leads. So if you multiply top and bottom by tan, the top, I'm not sure I want to distribute it. The reason is, in the end of this problem, I'm hoping to just have a tan on top, right? Which means I really want this to go away. So I can distribute the tan on top and distribute the tan on the bottom if I want. Or I can just distribute it on bottom. I don't have to do both, right? I can write it here and just leave it off back. So I'm going to distribute the tan to both of these, and that's going to give me what? The top still looks like this because I refuse to distribute. Yeah, if I distribute it, I'll probably have to take it back out later. The bottom is tan times 1 and tan times 1 over tan. So this is tangent theta plus 1. And then this cancels out, of course. So we did it. Tan theta equals tan theta. This is actually, I think, 2 steps shorter than my first attempt. Okay? But it required a little bit more creativity. Like, I had to think of how tan and cotan were related or whatever. I don't know, maybe not. Maybe it's even easier. Maybe it's easier to think about, easier to do. It just depends on your foresight. So it's totally up to you how you want to do the problem. You just can't cross multiply or that sort of thing.
If you were doing this proof for the first time, would you have to prove that tan theta over 1 is equal to tan theta?
No, that's a good question. Yeah, we would take that kind of stuff for granted. Yeah. Yeah, I mean, I suppose in some sense we'd have to prove that 1 plus tan theta is the same as tan theta plus 1 before we can cross it out, you know. But we have rules like commutative property of addition that allow that. So, okay, let's go on and try this one. This is another one I picked for you. This is a fairly hard one. I'll do one like this and then you try it. Okay, so we should probably pick the messier side to simplify. The only problem is both sides are kind of equally messy. This happens sometimes where you can't really decide which side is messier, you know.
Can't you bring a negative sign out to the front?
No. No, I don't want to. Here are some things you don't want to do, okay? What you don't want to do is you don't want to go like breaking this up into two parts, you know? This would be a really bad idea, doing something like this, 1 over cosine minus sine over cosine. Like, that's kind of fun, you know? Like, that made me feel cool when I did that. And it also is secant minus tangent. That's really nifty. But you just created two terms, and the goal was to have one term, and you had one term, and now you got two terms, so you're kind of working backwards. If you've only got one term on the right, you want one term on the left. You don't want two terms. Okay, so that'd be considered kind of counterproductive, to say it nicely. Okay, so let's go back to the drawing board with that. You know what I really wish I could do is cross multiply. Because if I could cross multiply, watch what happens. This would give me 1 minus sine squared equals cosine squared, which is basically just that Pythagorean identity on the left over there. It's really just that rule, pretty much. You know, so I'm going to have to do something to kind of fix it up. Maybe I could add 1 to both sides, or you know, add the sine squared over or something. But see, we're not allowed to do that. But that actually is kind of interesting to look at because it kind of tells me what I do want to do. If I'm not allowed to cross multiply, but cross multiplying would solve the problem quickly, then maybe I can sort of do the next best thing. Why don't I multiply top and bottom by 1 plus sine? I can multiply top and bottom by something. Multiplying by 1 plus sine here and 1 plus sine here is kind of like multiplying this over, sort of. So let's multiply top and bottom by 1 plus sine. See where that leads us. I like to call that the trig conjugate. Not allowed to cross multiply. This is sort of the next best thing. Multiply top and bottom by something. Okay, so what's 1 minus sine times 1 plus sine? Yeah, it's 1 minus sine squared. I'm not even going to distribute the denominator. Just going to leave it like that. There's two reasons I won't distribute it. One, I suspect I'll need a factor again if I distribute it. Two, I like the 1 plus sign there. See? Doesn't that match what's on the right? That's a good thing to have, right? Okay. One minus sine squared. 1 minus sine squared. Listen, over on the board here, we have some identities that we've been working on. These are all proven. We can manipulate these as much as we want. How about we write this as cosine squared equals 1 minus sine squared, and sine squared theta equals 1 minus cosine squared theta. Those are not new identities, they are just manipulations of this proven identity. Those are equations, do whatever you want with them. So I see that this 1 minus sine squared on top here is really just cosine squared, that's all it is. And obviously the cosine on the bottom cancels with this cosine right here, one of them anyway, and the top is now cosine theta, and the bottom is 1 plus sine theta, which was what we had on the right. I'd like you to try that same problem again. This time it'll look a little bit different. It looks like this. Try this one. Give me 1 second. It is secant theta minus 1 over tan theta equals tan theta over secant theta plus 1. Try that one. Try to use the exact same strategy I just used so you can practice it too. Questions?